There's one that says final, but
I realized that.
Pô, cara, a gravação lá deu pau lá, mano. Não consegui fazer não, cara. Não rolou, cara. Deu pau no ponto direito. Caramba, pau no ponto direito, pau no computador. Deixa eu sair daqui.
Okay, so now we're ready for our next speaker. We have Dr. Hubert Vonhof. He has studied and worked in the Netherlands, and since 2016 he leads a research group at the Department of Climate Geochemistry at the Max Planck Institute. The group focuses on quaternary paleoclimate reconstructions using archives like speleothems, skeletal carbonates, and lake sediments. And today he'll talk to us about paleotemperatures in speleothems. So.
thank you for that nice introduction. Yeah, so here I am. I'm going to talk to you about paleotemperatures, which is a thing that I consider to be quite exciting, in fact, in speleothems, because I believe lately there's a lot going on that is potentially bringing us forward. Ever the optimist, I'm going to show you some what I believe really interesting records and some new developments that I believe are going to be influential. We'll see in the end if this all works out. So I've put a few things together that to a large extent are not my personal expertise, but I'm working with people on several things. I'm likely to run into a few people here who know more about specific topics than I do. You can shout at me during the presentation if you want. And what I'm going to do is I'm first going to go through some of the technicalities, so some of the methods that we have, and then I'm sort of going to end into examples. And this is also because I never know where I end in time, and in the examples I'm just going to chop it whenever we're at 45 minutes. I even have a few extra slides that might be of help if I'm too quick, but I usually am not. Here we go. This is unnecessary information to all of you. If it weren't when you arrived here, it is now, because you've seen this in quite a few talks already, right? So we love Speleothem so much, not just because we like to crawl into caves, but there really are excellent archives, right? So this is super datable stuff, and the dating we've seen yesterday gets better and better and better. It's bloody amazing what we can do lately. And the other thing, and I'm an old carbonate sedimentologist by background, I have a marine background, it's calcite. We understand this stuff. We have proxy records. We're happy, usually, right? And so when I went into this as a paleo sort of oceanographer by training, I ran into this. I say, that's easy. You can do this and this and that. And then you find that it's not that easy at all, because all of these records that we unleash on this, they work, but trying to quantitatively distill the stuff we want, right? So the isotope composition of rainfall or temperatures turns out to be a difficult thing, because everything's connected to each other. We've just seen a nice talk about how everything is connected to each other when you look at carbon isotopes, right? And so this is the issue, and that's what interests me a lot, and that's what I'm going to steer into a little bit today. I always like to show this one. This is a Sorect record, and it's one of the not the oldest by far, but one of the older records that we have since I believe the first, this is a 2019 paper, but the first time this record was up and visible for all of us was, I believe, sometime in the late 90s.
98.
Oh, what is it? 98, right?
98.
There you go. And this to me is fascinating, because here we see what Speleothems can do. If you don't see that this is a paleoclimate record, it's time to leave, right? So this is paleoclimate, and it's beautiful. We see several things here. So we see beautifully from MIS6 to the Holocene, we see on the larger scale, we see these enormous nice swings that are glacial interglacial, right? So we say, cool, this is temperature, there must be temperature in there, this is Israel, huh? And so he said, sure, so we have a temperature record here, isn't that fantastic? But then you look one level deeper and you see these things that are marked as 1, 2, 3, 4, 5. Do you know what these are? Yeah, so these are sapropels, right, in the Mediterranean, right? And I'm not sure to what extent you know what sapropels are, but these are enormous perturbations in the paleoceanography of the Mediterranean. There's a lot of fresh water coming in, and around the Mediterranean it gets very wet. Yeah, so if I see a record like this, and you see that in the sapropels we get these very negative oxygen isotope values, that's not temperature, that's hydrology. And so this is our problem. We're looking at these beautiful records, and here we are. We want to understand what's going on, and we know that the parameters that we want to distill are mixed, right? So, and this is what we want to do. We've been trying that for decades. We have many proxies that work sometimes and don't work in other conditions, and this is what we're dealing with. And then I believe that recently we're making a lot of progress. There are a lot of very interesting things going on. Right. No, I'm going too quick right now. I'm still in my pep talk here, right? Because these are the people that I'm jealous of. If you have an ice core, you don't have this problem, because you can hold it and you hold your precipitation. And you do a straightforward isotope analysis. Ta-da! That's the isotope the composition with precipitation. And they're even luckier than that, because that analysis that you do also gives you the temperatures, because you can do, when you have an ice core, you can do this. That thing that says temperature there actually is the oxygen isotope composition of the ice. Yeah, so you get both. And this is not without assumptions, but it's pretty rock solid, right? Fortunately, these guys have one disadvantage that we don't have. It needs to be very cold to do this, right? So this is where I want to go. Okay? And this is where many people want to go. I mean, this is simply what we try to do with the Speleothem records to be able to disentangle those things, right? So I'm going to put something together today, which is about sort of my comfort zone, fluid inclusions, and my comfort zone would be the isotope analysis of that. But I'm also going to show you some stuff on this fabulous microthermometry technique that's going on right now, mostly still in Bergen, Norway, and Yves Kruger has been very friendly and sent me some slides. So you can see those. So that's based on the water, right? Then we have Speleothem calcite, and the one thing we can do pretty directly there are clumped isotope analysis. There are issues, but there are also movements towards solutions there. I want to briefly talk about that. And then the other thing is organic matter, and I really like this. I really like this. This is elegant, because we have a Speleothem, which we usually consider to be calcite, but there's water in there and organics as well, and we have several potential paleoclimate proxies here that exploit all of these sort of sub-archives that we have here. Okay? There's many, so I don't want to cut people short, because many more people are going into this with different techniques, but I'm sort of sticking to this right now. Also because I think they are quite independent. Let's be careful. Okay, a small picture there already of fluid inclusions, what they look like if you look at them in thin sections, right? You've probably seen the posters yesterday. There were a couple of very nice things there as well. I'm going to go through these methods quickly right now. I'm starting in something that's not entirely my comfort zone, but let's give it a try, right? So fluid inclusion, nucleation-assisted microthermometry. Who know about microthermometry here? I'm not surprised. Few more, yeah. The typical microthermometry you do on a sample, you make a thin section, ta-ta, off you go. and you have a thin section, there's going to be water in there, there's going to be a bubble in there, and you need that bloody bubble to do your paleotemperature, right? Now we have a little bit of a problem, and I'm going to go into that with Speleothems because it doesn't have that bubble, right? So that's the challenge. How do we deal with the fact that we don't have a bubble? There are simple solutions for that, fortunately. And there are some requirements. You need really well preserved fluid inclusions that are still in their original sort of state. Let's have a look. So slides by Heath, right? So he's the expert. Fluid inclusion stalagmites, we have one there. Typically we like to think of them as primary, so there are no secondary phases simply because not too much is happening to them after their formation. And they contain obviously relics of the drip water. And we like the drip water because that tells us a lot about the climate. But in this particular case, we like the drip water in this shape because we can do microthermometry if we do it right, and we can get the cave temperatures. So they are typically monophase, and that's where our problem is. We don't have a gas bubble. But we can play with this quite nicely because the density of the water is the parameter that tells us the temperature. If we can get the density out, I see some frowning there. Tell me, yeah? Yeah, I'm still okay, good. And it's a very simple physical principle. This is cool, okay? So we're going to try and figure out how that works. And so the problem is we don't have a gas phase, right? And here you see a sequence of events, and I've seen the same photograph on a poster yesterday, right? And what happens here is you have a sample, and let's start at the left side, 20 degrees Celsius. This is your lab, more or less, right? And you're looking at it through the microscope. You see a liquid, and that's it, it's liquid, right? And then you start with bringing the temperature down a little bit to 10 degrees Celsius. And it still says, oh sure, I'm a liquid, so it stays a liquid. But then you tickle it. And you tickle it by shooting at it with a femtosecond laser. And what you then do is you kick it actually, right? And then you provoke the formation of a little bubble. And that bubble sits in there nicely, and then from there, you bring your temperature up again. And by the time that your bubble disappeared, at that temperature, at that precise temperature, that's the homogenization temperature, is the temperature where that was the formation temperature of the fluid inclusion in the cave. There is a little bit, such great slides, there is a little bit of a correction needed to go from that precise temperature that it disappeared to the cave formation temperature, but that is based in a very solid physical model actually. Simple, huh? Equipment you have in many places, but you need a laser in this particular case to get that right, and not many labs have that, right? So this is the typical equipment, and in the back you see the laser. I'm not going to spend too much time on that because if you really want to know more stuff about that, there are people here who actually work with it and have much more expertise in it. But it's a cool thing. Some more important things. Oh yeah, he even provided us with is it working? Because this is a little movie, and that's not working, forget it. Yeah, there was a movie here in which you could see whoop, the bubble appear and move around a little bit, quite nice. Okay, fundamental assumptions. Density depends only on the cave temperature, right? The fluid inclusion is a closed system. When you start messing with it after the formation, you change pressure and things like that, then you're screwed, basically, because your temperature doesn't work anymore. And then, of course, there is this assumption that the closing age of the inclusion has the same age of the surrounding calcite. It's very difficult to do that differently. And then for the model, it needs to follow the thermodynamic rules, essentially, right? So this is quite simple. What's cool about this method, if you really think about it, if you do this right, you ought to be able to do it on a single fluid inclusion, right? Which makes me jealous from the isotope point of view. But fortunately, next slide. If you do it on a single inclusion, it's not going to work so well because you have to do multiple and form these sort of Gaussian distributions and then get averages out. So you're going to have to do statistics here. So it's not that quick. And I believe that I talked to Eve about this sometimes. I don't know if he entirely understands already why the spread is there. But it doesn't really matter because the technique works like a dream if you just do the statistics on it. Okay. Is that kind of okay for the, yeah?
That's very good.
Yeah. So we stayed in fluid inclusions, but moved to my comfort zone, right? So we're going to be slightly more destructive right now, because I'm gonna I'm gonna make sure that Eve cannot do anything with them anymore when I'm done, right? So we do the isotope analysis in fluid inclusions, and we need many fluid inclusions to get that right. What's nice about it, it gives you very valuable and very direct hydrological information. It gives you the oxygen isotopes and the hydrogen isotopes of your drip water, and we like to think that that actually is rainfall from the rock decay. We can get to paleotemperatures, and this is why I'm showing it here, if you assume isotope equilibrium, haha. But it works in some cases, right? So you then do the oxygen isotopes of the calcite and the oxygen isotopes of the water and temperatures. There we go. They contain the typical Speleothem up to 0.1% of water, which doesn't sound like much, but if you have a kilogram of Speleothem, we often have that. That's still a gram of water, right? That's pretty good. And of course, we think that the isotope composition of that water, we've already looked at the temperatures from a physical perspective, that is the drip water, and we actually believe that that represents the paleo rainwater recharging decay. Okay? So we should be able to look at past changes in isotope composition and rainfall. And if we think that we are able to do the analysis, we should also consider that we probably find our data in hydrogen and oxygen isotope space on the global meteoric waterline. To what extent is the global meteoric waterline a known phenomenon here? People don't know it? God, you're good. Everybody knows it. So, very briefly, this is it. You know that, right? So if I do my analysis on fluid inclusions, I really want to find myself on that line, because then I know that I haven't screwed up either the oxygen or the hydrogen isotope analysis. Okay, cool. Let's not talk about the processes too much, because you know that thing already, but it's really cool to know where you are on that line in general, because depending on the climate that you have, you're going to be on a different place on that line. So it's really nice direct information. Okay. This is my own not so nice picture of what fluid inclusions look like. This is a thin section picture, and you see quite an interesting pattern. It kind of looks like that. So you see these lines, which are growth lines, and the fluid inclusions tend to sort of group on that. But if you look in a little bit more detail, you see these verticals where the arrows are. There are vertical bands there, which essentially are the crystals. And if you really look, you may not see it too well in the back. There are some color changes there, and there was a tiny fluid inclusions in there as well. So quite heterogeneous. But we have reason to believe that it's all the same water that sits in there. So when I try to hammer this and get the water out, it shouldn't matter from which fluid inclusion I get the water. Okay, that's the point here. So how to get it out? Sorry, this is my slightly corny joke, but we're not the first to think about this. So this is the biblical story of Moses striking water from the rock. And I always make the joke that I like my lab to look like this, right? The old man climbing up the rock with the hitting it. And well, okay, but we have all sorts of health and safety issues if we do that. So, so we're going to go in a much less romantic, right? This is kind of how we do it. We have crushers. We have these little toys in which we can put samples, and then depending on the analytical apparatus that we use, we put those on vacuum, or we send a continuous flow of nitrogen or whatever through. And in that flow, we then crush the sample. The idea is we do that just above 100 degrees Celsius, so it all goes in vapor phase, and we transport the entire sample to the analyzer. Sounds simple, but let's have a look, right? So we typically need half a gram or a gram of material to get enough water, so 0.2 microliters, so 200 nanoliters is sort of the amount that most labs need, or slightly more even. You get hydrogen and oxygen isotopes simultaneously. I've said that 4 times now. We believe that represents paleo rainwater. And our problem is, of course, that we always have to defend, does this really preserve? So is it well preserved to begin with? And when we get it out, do we fractionate it? Right? So these are the things that we worry about. So many people recently working on this, which is really great. Our own work, I don't expect you to see anything in these two things. It's just a square on the left and a square on the right, and these are 2 different analytical approaches that we have in our lab. On the left is my own approach, which is based on a real mass spectrometer and a TCA, and then on the right, the slightly more fashionable picaros. And the picaros is more or less where we're moving to, because that seems to be the thing that currently produces the best data, right? So we had a comparison of the two systems in our lab by Stefan de Graaf in 2020, and so he ran samples on both of these systems, and you get very boring pictures from that. So on the left we see a global meteoric waterline, and the dots on there are different speleothems from different places that we crushed, and this is just to hammer home the point that when we do this, we are able to put stuff on the meteoric waterline, which means we don't screw up badly when we do this analysis. This is an important point to make, right? And then Stefan did it on both machines, which are fundamentally different. And then, so the right plot's even more boring. There is a one-to-one, and basically there to tell you that it doesn't matter on which machine we run it. They both do it. Okay? So we seem to be okay with that. So that, I think, yeah, that was the boring bit about fluid inclusions. Examples come later. Text 86. Way out of my comfort zone again, right? So, organic geochemists in here? Anyone? A little bit there, right? Okay. Well, I know enough about it. It's okay. We actually do this right now at Max Planck in the lab of Alfredo Martinez Garcia, who is, from my humble perspective, a very gifted organic geochemist, and he's doing a lot of that stuff right now. So several people here, Marcela, for example, working with that. And I believe it's a promising thing. Do you know Text 86? Yeah, quite a few people should, right? Because this has been there for 20 years already, and it's a great tool in paleoceanography. Everybody uses it, right? It's not so well known for Speleothem, so I'm going to explain a little bit where we are right now. Okay, there are glycerol, diacyl, glycerol, tetrahydroxyl, GDGTs. That's why we always call them GDGTs. It's very difficult to pronounce the entire thing. And they are produced by archaea, which are some sort of archetypal bacteria. They're basically everywhere. And it was originally used as or proposed by Stefan Schouten in 2002 as a great temperature indicator in paleoceanography. You measure that stuff in marine sediments, and ta-da, you have temperatures. It's very promising for speleothems, but it's not much used yet, and that has to do with the fact that until recently you needed a lot of material to get an analysis out. Simply impractical. Okay? There's a very good thing about GDGTs, they're virtually indestructible. So even in the marine sedimentary record, they survive. You can get temperatures out of the Cretaceous. Whether you believe them is the next question. But in principle, this stuff is quite sturdy. Okay? The working hypothesis that I'm on right now, and that's not entirely uninformed, is that these archaea live in caves. They live on the speleothems, record the temperature of the cave in their GDGTs, and then conveniently die or get entombed, more or less, in speleothem calcite for us to take them out and analyze them. Okay, that would be it. Okay. Here they are. So very nice wiggly organic molecules that we have there. So these are all GDGTs. You have to look very carefully. So you see them 0, 1, and so on. And so the difference are these pentane groups. You see these sort of pentane groups are in there. And so the difference is that they have more or less pentane groups. And what Stefan Schouten did initially in 2002, he realized that the composition of these different GDGTs in these membranes, because they are membrane lipids, sorry I didn't tell you that, so they are compounds in the membranes, in the cell membranes of these archaea. And these archaea, they change their composition of these different GDGTs with temperature. And that it's simple because it has a physiological sort of function for these bacteria, and they try to optimize the composition of their membranes essentially by changing whatever that composition is. And the simple thing that Stefan did was he said, oh, cool, let's look at that, let's do a calibration, and then he came up with this relatively simple ratio, in fact, between different GDGTs. And ta-da, that was temperature. And that still is how we do it today in paleoceanography, right? This thing requires a calibration because you get a TEX86 number and you need to know what temperature belongs to that. So this is how this started with a calibration that Schouten et al. In 2002 produced. Okay, is that more or less? No? Okay. The cool thing is these archaea, they also exist in caves, right? And there was, I think the first paper that we know of is by Yang et al. In 2011, who looked in one of the Chinese caves and found them. And they also registered that the changes in TEX86 went together with changes in the oxygen isotope. So, oh, that's interesting. But when they tried the then marine calibration, they got the wrong temperatures. Okay. Then Alison Blythe, who was working with Stefan Schouten in 2013, stepped in and did a lot of work on Speleothems. And actually, it's her work later sort of polished up in the paper by Andy Baker, and Alison was in that. In 2019, is what provides us with the now accepted, you see that on the right, calibration curve for Speleothems and TEX86. So this is how that stuff works. So this is the one we're still using. And this is what we're doing now at MPIC. The gray dots that you see there, same calibration curve, are the existing ones from the Baker et al. Paper, and the red dots are the new ones that we put in. There are many people that have provided us with Speleothems, so thank you all very much. And it looks like we confirm the existing calibration. We've made it a little bit better towards the edges, and it seems to be very robust, actually, right? The other important thing that Alfredo did, and that's in blue on the left-hand side, he brought it down to a gram of calcite from anywhere between 5 and 15 grams that was needed beforehand. And this is super convenient for us because I need a gram for the fluid inclusions. So what we do is we do the fluid inclusions first, we take the residue, and that goes straight into the TEX86. And this is how we currently run our business. Okay? Cool. We stay on the slightly boring side of explaining the techniques. We go to clumped. I stay way out of my comfort zone, but clump people, we have a few here. I talked clumped isotope analysis, I think you all know, right? It is a somewhat funny way to look at isotopes, at least if you are used to the normal conventional isotope stuff. It feels a bit weird. It is analytically challenging because we are used to looking at masses 44, 45, and 46, which are the common masses for looking at CO2. But these guys, they take 47 on, which is a doubly substituted one, very rare, so tiny peaks. And if you really are a masochist, you also try cap 48, and then you have doubly substituted oxygen in there, even a smaller peak. And you are operating at the lower limits of what our mass spectrometers can do. Okay, so this is specialist work, but super interesting. The cool thing, of course, is you can get a temperature from a carbonate isotope analysis, and you can say, I don't care about the water. Because that's what we normally need. We need water isotope data, do the equilibrium. They don't have to do this. It's built in, so that's cool. Okay, how does it work? I explained a little bit already. The cap 47 is important here. That is an isotopal log, so that is an isotopal log is a molecule with a specific isotope value. That is 13C, 18O, and 16O. So we have doubly substituted the heavy carbon and the heavy oxygen. And that gives us direct temperatures if you do the right calculations, right? And then you could do a similar thing with cap 48, I mentioned. More difficult. Some first work is out, published recently. The trick, as I'm going to try to show you in the next few slides, I hope that works, is the combination of the two, because that resolves the problem that we have in Speleothems. What's the problem that we have in Speleothems? Roughly this. Weiner et al. 2011. The cap 47 on the y-axis, and let's say fractionation on the x-axis. The x-axis we get by doing fluid inclusion isotope analysis. So we get the oxygen from the fluid, we get the oxygen from the calcite. You can calculate your 1000 Ln alpha. And if this thing would be in equilibrium, then that line that you see there is where all the data is. If it's kinetically well, some people would say screwed, but kinetically affected. For speleothems, typically we go to the right here, right? And then you can imagine that if you don't correct for that and only take the Cat47 value, then the lower two data plots you get to temperatures well above 25 degrees Celsius, right? But in this particular case, in this cave, it's been established based on a modern sample where we simply did the temperatures out, that's the wrong temperature, and brought it back to the line. That the vectors to bring it back to the line actually are these vectors that are in there. Yeah? So if you correct this correctly, you get much lower temperatures. And this is precisely what we see when in clumped isotope temperatures we get kinetic effects. They typically go to higher values, higher temperatures, sorry. So this is a way to correct, but there's a drawback here, because you need to assume that your modern system, the kinetic fractionation in your modern system, is the same when you go down back in time. And I believe that we all understand here that the chances that that happens are not very high, right? So we have a bit of an issue there. So that's why you can, the Cat48 is so important, because you can make similar plots with Cat48, and Cat48 allows you to get these correction lines in based on simple theoretical considerations, which are clumped isotope internal. So you don't need to have that information on your kinetic fractionation. That's the idea. Very new, just few papers out still. And then when you do that, it looks like that. So David Peinay, Jens Fiebig, I believe that Peter Swart has been writing papers on this as well. And essentially this is what you see. So it looks very much like the previous slide on the left, but now the x-axis is that Cat48. I'm sorry, I ripped this from a publication, so it's impossible to read in the back. So the left slide says Cat48 on the x-axis, Cat47 on the y-axis. And you see that line there, which is the equilibration line. And they assign the processes. They say if there's CO2 degassing, you see that red arrow? You go this way. Well, guess what? Speleothems, degassing, of course. So typically driven off the line in this direction. And that's also what you see in the right-hand plot. The two squares that we have on the lower right-hand are Speleothem samples, and they are kinetically sent down into that lower right-hand corner. And the idea with the combined Cat47 and Cat48 is that you can correct for that without prior knowledge of what the hell the kinetics are doing. And that is because the Cat48 and Cat47 react differently to kinetic fractionation. Okay? The math behind this is way beyond, right? But this is the trick right now. And we have some data that we ran in Jens Fiebig's lab that suggests that we're actually doing it right, that the comparison of Cat47 temperatures only and the combined Cat47 Cat48, that the latter are much better. Okay? We don't know yet where this is going, but I think it's super interesting because this may be our way to getting good clumped isotope temperatures from Speleothems. Where am I in terms of time?
20 minutes.
I got 10 minutes left.
No, 20 minutes left.
20 minutes left. Jesus, good. Okay, so I was faster than I hoped. Okay, that's good.
Oh, sorry. 15 minutes.
15 minutes. Then I'm on time. Good. Okay. Because now I'm going to relax right now. Cheers. We're in the examples. So this is the point where I can drop it wherever I want. Right? And the examples are a little bit of a mishmash, but I'm going to try to turn them into a sort of consistent story. It says, yeah, this is actually quite correct. I have 4 examples in total. The latter is not so much on temperatures, but it's a record we're very proud of, so I want to show it anyway. And the first ones are, the Borneo work really isn't my work because that's really hosted in Bergen. And that is a really cool data, by the way. You're gonna like that. And the first one is my own old first fluid inclusion isotope data. I just show that because there the temperatures actually worked without us knowing what we were doing. That was quite good. And so let's just go in there and work our way through. If you have questions, if it's unclear, just kick me because now we really are quite. At least we are very relaxed now because nothing's happening. Ah, here we go. I guess it's fine. Cool. We had some issues, I think, with the conversion of the. You had some issues as well yesterday, right? Oh, this was a slide. It's okay. Well, actually, it's not, perhaps. Okay, I'll just talk you through it. The white slide. Let's put it on. What you actually see here is an amount of data from a cave in Peru. It's the Cueva del Tigre Perdido record. I think you can do the translation. And this was a site that we visited quite a while ago, and we didn't do much there apart from picking up. I mean, Chico, this was a typical example. It was a vandalized cave. So my PhD student was there. I said, okay, well, let's take these two.
I went there too.
Yeah, yeah.
Very vandalized.
That's crazy.
Nice.
Yeah.
I like nice.
Yeah, yeah. But a beautiful record. He literally picked up two pieces, and we couldn't even connect them. And then he dated the entire thing, and then it turned out to be the entire Holocene. And we've been working at other caves in the region, and we couldn't get that anywhere else. So these two that he just picked up like that, that was it. So we decided to work on that. We had the Holocene there, and we were in the beginning stages of the fluid inclusion stuff that we were developing at that point in time. So the old technique with the mass spectrometer. And we thought, okay, let's give this a try. So we did that, and the material was really well behaved. So we ran the data, we plotted it in the hydrogen-oxygen isotope space, and it was smack on the global meteoric line. It was awesome. We didn't know what that was, but it was interesting. We had the Holocene, we knew that, but we had quite a lot of isotope variation. But all along the meteoric waterline, so that's interesting, right? And then I think we go to the next slide, because here I can attach that, because I showed the meteoric waterline behavior in the previous slide, and now we just put it on the time axis, right? And then you see that if you take these same data and you compare it to the calcite oxygen isotopes, which is the kind of wild red dotted thing at the bottom, and the insulation curve right above, that's what you do when you're trying to publish this. Then you see that the entire thing is in phase, right? So that's interesting. So quite a lot of isotope variation. Huh? So there is like it's more than a per mil, almost 2 in the calcite, and same in the oxygen isotopes of the fluid inclusions, and even more in the hydrogen isotopes. So this was all super consistent. So we were very happy with this. I still am. And then we thought, oh, cool, because now we have water calcite, let's do the temperatures. This was one of the first times that we actually got the temperatures right. And I've had many times later that we couldn't, right? So the temperatures here look like this. It's a nice story because we would now use equations like Tremaine, for example, or there are a few others, but I usually go back to Tremaine. That's kind of a fine record for me. At the time we didn't have that, right? The thing that we did know that if you used Kim and O'Neill, which was let's say the paleoceanographical thing to do, that we would get the wrong temperatures very big time. Right? And then so we played around, and they ended up with Craig 1965. Does anybody know that? Do you know that? It's not a very good. But it gives you completely different temperatures if you compare it to Kim and O'Neill, right? And we knew that we had to go in this direction, so we said, let's do that. We put that in. Of course, we got the questions, why are you using Craig? But since that time, this problem is solved because we can go to Tremaine that gets more or less the same results. And here what we saw, we got quite nicely temperatures sort of circling around the modern temperature in the cave. You can also see that there's quite a bit of isotope variation, which I think is realistic. If you add up all the uncertainties that you have, it's simply not so super precise. But this was a cool first thing where you can see that when your isotope values move around quite a lot, but you can show that it's all in the hydrology, then the resulting temperature should indeed be kind of flat. And this is the whole principle that we have here too, that we're talking about. Okay, so that's why early work not super precise, but nuts. It was a good indication that it works. So from there, let's go straight into how often it doesn't work. This is work in my lab on a cave in Belgium. We're actually trying to publish that right now. And here you see a global meteoric waterline. The dotted blue line is a local meteoric waterline, and you see a bunch of data, which are all speleothems, different ages in that cave. And we've run the fluid inclusions on it, and then you see that fortunately there is a big chunk that sits on the line, but then you get that sort of pew thing going off to the right, okay? And that one we didn't like, and you're going to see in the next slide why we didn't like it, and we thought that's odd. And then we observed that when you go off that line to the right, we also increasingly, or decreasingly I should say, we got less and less water per gram calcite out of this sample. So it was, when there was less water, we were off to that thing. And then you can do that, you can take these data and do temperatures again, and then the blue horizontal line there is where we like the temperatures to be. So we see we have a lot of temperatures there. The lower ones could still be okay. That could be more towards glacier conditions. It's not. We're still working on that. But you see that thing like pew shooting off to the right, and then the top temperatures are nearly 40 degrees Celsius. We're in Belgium here, huh? So that's not happening. That's not real, right? And then recent work from the Bergen group that I was involved in looked at these things, and what we actually believe is going on here is that we have an analytical artifact that we have in our systems here. And that is that when you have a sample in which the fluid inclusions are not sealed off well enough, what we do is we bring it from 20 degrees Celsius to over 100 degrees Celsius, and we keep it there for half an hour before we do the analysis. And in that time, we build up pressure on the fluid inclusions quite dramatically. And if they don't seal well enough, you're going to be losing a little bit of the water through diffusive pathways. And if you don't lose it all from a particular fluid inclusion, you're going to be fractionating like hell. And that's what the fractionation looks like. Okay, so this is there's a super interesting paper, I think, from Fernandez et al. 2023 in GQ that shows this. And actually, he also shows a way to correct for this. So what you can do, you can try to, oops, no, of course, this doesn't work the way, yeah. You can try to just correct back along the line that you're on, because the slope of that line that you're on has to do with in your technical device has to do with we use a moisturized gas that we send through, and the humidity of that gas determines the slope of that line. And so, nice paper if you're interested. It's a bit geeky, and here we go. But so here's a problem, right? That we see pretty often. So you really have to check whether you're on global meteoric water lines or not, and when you're not on it, you really have to check whether it's okay that you're not on it, or whether you have things like this going on. The other thing that is, of course, in permanent discussion in the field, I mean, these are tiny amounts of water in large amounts of calcite, so they are vulnerable to diagenetic exchange, and so you have to worry about that. I must say that from my personal experience, we don't find this problem a lot. And this is the work by Uemura et al. In 2019. It's quite a nice experiment, but they heated samples up like mad. For I think more than 12 hours, and then you were beginning to see these shifts, right? And so the conclusion of Uemura was as well that, you know, the way we're analyzing stuff right now, we should not have an issue with this, right? But it's something to keep in mind that this is possible. And the other thing is by Demony et al., for example, this 2016 paper, the possibility that we have intermediate phases like ACCs and things like that that are in the game here that could produce offsets away from equilibrium. I think that Attila himself says about that's less likely to happen in the low latitudes. I don't see it happening a lot either, so these are things. But just for you to know that these are things that are on the table. Okay. Is this running up or down? So how many minutes I have left?
You have about 5 more.
5 more, okay.
Yeah.
I can do this.
This is the time.
I can do this. This is cool. So this is the Fernandez et al. 2023 paper, and it has a technical component to it, and it has a data component to it. These are the data, and so the triangles that you see there are based on the super nice microthermometry technique, and it just gives you an idea on how precise this is, right? These are time series. And then what's good for me is that there's also fluid inclusion isotope data in there, which is fluid inclusion isotope data from Bergen, a similar system to what I have. And you here see that it matches amazingly, right? So here, this is a typical example that if you throw 2 techniques at it and see what the temperatures do, if you find stuff like this, you're very happy, right? It seems to work. What is interesting is that on the lower 2 graphs, the left one is the corrected one, and that is the corrected one of this isotope effect that I just showed you in the Belgian data. So, yeah, so corrected back to the along this line to the global meteoric water line, and then calculate with that value. And then you see, compared to the uncorrected stuff, because there also is a huge difference in water yield between here and there, much less water there. So it looks very much like this stuff we see in the Belgian stalagmite. Sorry for running around so much. Here you need to correct the data for the fluid inclusions to come to the right temperatures, and the microthermometry temperatures are guiding us in how we need to do that here. So this is quite cool. Yeah. So the correction is an honest correction. We're not just pushing it back to these temperatures, right? This is really pushing it back to the meteoric waterline and then calculating. So this is really cool, and what you see in these data as well, I think, so this is a Borneo Speleothem, some of the publishing super nice things on that lately. You can then compare that to all sorts of climate variables, and here you see what amazing precision we have in that, particularly in the microthermometry and how that follows, let's say, global scale temperature things. So here I really believe they've nailed this problem of getting the temperatures right and singling them out from the rest of the data. Okay? Yanyang, China, we were talking about that. So this is published by Jasper Wassenberg, who was in my group as a postdoc over the past few years. He's in South Korea now, doing very interesting stuff as well. This is an example where we have looked at monsoon response to determination between MIS 6 and 5, and we're using TEX 86 data, so I should show you some TEX 86 data, and I believe this was the first really long serial record of TEX 86 data that was published, and it has a direct comparison with this dual clumped isotope temperatures in there. So let's just go in there quickly. The whole idea about this paper is that we tried to sell that there was a southward shift of the Indian monsoon in the coldest part of MIS 6. And we observed that in the fluid inclusions, which you see in the bottom panel here. It's kind of small, sorry people in the back. But in the top panel, that's where the important thing is for the talk today, because those are the temperatures. And there you see in the dark blue dots, we have TEX 86 temperatures, and then they go in the light blue dots, that's still TEX 86 temperatures. They're two stalagmites. They have overlap, and the overlap matches. And then you see these two things with the huge error bars. Those are the clumped isotope data. And so the point here is that they're on the mark, right? But they just have a lot of, a lot more error bar. And this is typical. So the clumped isotopes, because it's so difficult to measure, typically have slightly larger sort of error bars. And I would say that the microthermometry, but to some extent also the TEX 86, we can get much more precise in. And then, so the combinations of these things, that's really what I wanted to show you here, the consistency of the combinations of these things. I can also say here that the fluid inclusion isotope data to a large extent also give the right temperatures. There's one zone in the coldest part where it's offset, but we believe we know why that is. I'm not going to bore you with that now. If you want to know, you can ask. But so quite a consistent data set with these new techniques, which I find very close. This is the one I just wanted to show you because we're proud of it. And this is more about dating, actually. This is a record that has been shown in different places, so some of you have probably seen it already. This is the work by Monika Markowska. And that's a Saudi Arabian record that we're working on right now. It is relevant to this talk because it's about fluid inclusion isotopes, and we are working on the paleotemperatures. But the fluid inclusion isotopes tell us a nice story, and what is very cool about this is that this is a really long record. We go back 7 million years that uranium lab dated, and it's a fabulous record in the middle of the desert, right? So that's neat. So I'll show you quickly what we have there. This is more or less what it is. So 2 examples of the typical Speleothems that I picked up there. You know, you go into a cave and you're in the desert, sand camels, and you go under and then Speleothems. It's crazy. And the data on your right-hand side, on the right-hand side here is, so look at the bottom panel because the top, the stuff on top is more decoration for the publication. You see in box plot sort of style, you see the oxygen isotopes at the calcite. We go back almost 7 million years. There are a few gaps. The gap I like most is the one that has the Messinian salinity crisis in, which probably was regional drought. And then we see that we keep getting back these wet periods in between, of course, dry periods in this desert, right? And you can see that in the oxygen isotopes we're going up in these values. We've heard a lot about that, so you should probably say, yeah, it's drying up, and that's what we expect because there should be a drying trend from the Miocene to the modern, and this for the first time documents that in the wet events in that desert, right? So this is the cool thing there. And then we thought, okay, yeah, but what precisely does it mean? So we ran the fluid inclusions, and I think I'm only showing this really to show you that we can go back 7 million years in time and get fluid inclusion isotope data that I really believe to be original. Yeah. And this is the cool thing of speleothems. It's like putting rocks in a wine cellar, right? I mean, there's no better place to store calcite than a cave, eventually, right? And if you're lucky enough, because I picked those up, and I quite literally, they were still standing there. I had no clue when I got them, so okay, I could take this one, I could take this one. And I'd just taken something that had been sitting there for 7 million years. That's crazy, right? But anyway, the point here is that I think the important issue here is that we have a lot of fluid inclusion isotope data. We can put that on the global meteoric waterline, and you can see a time trend through it. You see the color scheme on the right. So the old stuff, the Miocene and Pliocene stuff, sits at very low isotope values, and then we gradually go up. And at the very top, we have the modern rainfall data. So here you see in the isotope composition of rainfall how we go through this drying trend over the 7 million years that we have here, right? And how the only real way to interpret this is that at the start we had large amounts of monsoonal, so the ITCZ reached up all the way in that part of Saudi Arabia, much further north than we could do right now. But that was because we didn't have ice sheets in Greenland, right? And so this kind of fits the pattern, but this is the first time that we can really couple this to atmospheric circulation patterns. So this is not so much temperature right now, but it is hydrology. And if we understand hydrology, we get a better grip on temperature as well. Okay? Okay, and now hurry through the rest. I am Tete. Yeah. Here's my summary. Yeah. I think there's significant progress over the past decade. So in how we are inching towards getting better and more quantitative paleotemperatures. The one thing I want to say to you, if you want to try to get them out, try to do multiple ones. And if you're able to show, and that's so cool because they're based in different archives, right? And if you're able to show that they are consistent, then you're doing the job right, I would say, right? So this is the thing. And I'm just going to leave you. Every technique has its drawbacks. This is a slide in a paper from Nele Meckler that we wrote for Elements. And this is like a nice overview of what we believe right now is typically what we can and cannot do. Everything in blue are some of the other options that I didn't talk about today. Okay. Here we go. That was your special issue, Kathleen. Thank you.
Okay, thank you, Hubert. That was great. I'm probably biased, but it's fun to hear.
Keep it that way.
Do we have any questions?
I wanted to ask, after post-entrainment, to what extent can you see the exchange between fluid inclusion and calcite, and how can you correct for that?
Okay. Shall I repeat the question for online, or is that? Yeah. So the question was in fluid inclusions, if post-depositional exchange between water and calcite occurs, to what extent do we see that, and can we correct for it, right? Okay, so the idea is you will only see it when it happens at a different temperature than the formation temperature, assuming that it's an equilibrium process, right? You can exchange whatever you want. If you haven't changed the temperature in between, the difference is going to stay the same, right? So then we don't see it. But if, for example, you have fluid inclusions from an interglacial and then you go to a glacial and you start exchanging, you should see something. What will happen then is that you're going to change the oxygen isotope composition of the water in the fluid inclusion, but you're not going to touch the hydrogen isotope composition. So you're moving away from the meteoric waterline. This is another reason why the meteoric waterline is super important. When you're on it, you know that you're probably okay, and when you're off it, you have to start worrying about why you're off it. Yeah, so that would be what you see then. I personally don't see it a lot. What I see much more is this issue when diagenesis occurs, is that that the sealing goes bad, and then that we start losing through diffusive transport. We start losing water, and then we get these funny offshoots to the right. But it exists, of course, right? Let's be clear about that. Yeah. Yeah.
to the similar detection question, like when fabrics are open, so you like assume like there is evaporation loss during in analysis time.
Yeah.
So same can also happen. Like your water can also percolate through the speleothem because it's
Yeah.
like thousands of years. So
Yeah.
you just mix water from very younger water
Yeah.
percolates through the
Yeah.
and goes down. So how do you take care of that?
Probably you're going to get trouble analyzing that stuff. So the question was, if that diffusive loss effect occurs in your analyzer, it can also occur in the cave already, right? That's
Yeah,
what
yeah,
you're
yeah.
pointing
Yeah,
out.
yeah.
And how do you know when that happens, if it happens? I would say that first of all, I would expect that when I then try to analyze that stuff, I'm going to see this diffusive stuff even worse. Probably we're going to get patterns out there which are flat isotopically or something like that. It's difficult. Huh? It's again, what we always try to do is we select material, right? So you look at the petrography. Just Andrea's going to show us a lot more about that, and you're able to see what is the good stuff and what is the not so good stuff. So if you already know that you're in the not so good stuff, you're simply going to be a hell of a lot more careful when you analyze these things. I hold on to the meteoric water line because that tends to get screwed up when you have things like this. Yeah?
If you hit, you mentioned that you hit the samples for 100 degrees for 12 hours.
Yeah.
For someone who's more.
Yeah, that was Uemura, yeah.
It's not evaporated, the water. Evaporated?
In his experiment, he says no. And given the fact that he seems to be going out on a horizontal line, well, in this case, it's a good question. I don't know. He wrote this paper before we started thinking about this diffusive loss. And at the time, we were only thinking about in situ diagenetic exchange. And thinking about the diffusive loss is something that we started picking up later because our instrumentation got better and we saw these lines and so going on. And so that is so it's not impossible that he saw that, but I don't know.
My point of view is will be evaporated. And because the sample is still remain and they have no days to go, will be condensed and will go to liquid state again.
I think it
But
is.
it
Yeah.
will be changed the homogeneous degree of that's what.
So
That's
I
the
think
point.
I think in his experiment he'd pump it off entirely, and if he would evaporate whatever he opened, let's say quantitatively, then there's no isotope effect. The isotope effect, the way we see it, of course, is because this diffusive escape that we have in our experiments is not complete. So there's just a little bit of water going out from these fluid inclusions, and there's part staying behind, because otherwise, quantitative conversion, no isotope effect. And so this is maybe, it's difficult because the experiment that Uemura did is not very comparable to the experiments that we did, the observations that we made in our pressure systems. Yeah.
So if you're talking about successful rates, do you see any correlation with like the crystallite, or like there is a threshold that you would say,
Okay.
and why not aragonite?
Okay, well, so deep in my roots, I'm a very lazy man. So, and I think many of us are actually. So quite often, when we have a technique that works, we don't ask too many questions. But right now, we're also it's about method development, right? So we're now getting into this stage that we're beginning to understand that there are artifacts, right? And so my short answer to your question is, we should not be analyzing stuff that we do not know the petrography of. But Andrea, I see you nod. But I believe the thing is, until now, we've simply done that. And so we just say, oh, you have a stuff, come on, let's give it a try. And because it was quicker to do the analysis than to get a thin section first and da. But we should turn that thinking round. We should really now start looking at understanding the petrography. What I didn't show you in the Saudi Arabian stuff, you might like that, Andrea, is that this long drying trend that we have in there, right, over 7 million years, it is mimicked in the petrography. So we can see the petrography change through that thing as well. I mean, not 100%, but it's very clear, and that you can see that the petrography is changing towards stuff that is in more dry environment. So this alone is a reason to look at the petrography. But when you look at the fluid inclusions, it probably is even more a reason, because you can not even do the analysis if you already know that it's useless, right? Yeah. Problem is we're quick now. Huh? We can do easily 10 to 20 analyses a day right now. So usually we just say, oh, let's go, and then figure out later. I fear it works that way. Yeah.
Do you have a question? So if you have two temperatures given from one from clump and the other from fluid inclusion,
Yeah.
and let's say they don't match, like in my cases, they don't match some
Yeah.
of them.
Yeah.
So which temperature should I trust more? Because because the processes that may be causing the fractionation in clump Cat 47
Yeah.
may also be causing fractionation
Yeah.
in the 18 of the water
Yeah.
and the fluid inclusion. So
Probably my official answer would be I would try a third paleotemperature and see if it fits with either of the other two. This is difficult, huh?
yeah.
This is difficult, but I think that's one of the core messages that I have for you, right? If it is worth it to try and pin that thing. I showed you the data from Jan Jung, right? So we had this beautiful text data, and we were woohoo over the moon, right? And so we're going to publish this, and of course we did. And but then we thought, oh, wait, because we might still have to defend that we can do this. And so we went to Jens Fiebig with two samples, the coldest and the warmest. And he then showed that was within error, what he got. And then we said, thank you very much, Jens, you're on the paper. But this is the way to go, I would say. I think it's still necessary to because we know every technique has its disadvantages, that we try to make it more solid by going to multiple. That would be the idea.
Okay, any more questions?
Coffee.
Okay, thank you, Hubert. That was great.
My
great.
pleasure.
Oh yeah, one more. Quick announcement before the coffee break. If we're gonna take down the posters now from yesterday. So if you want to take like a picture with your poster or anything, you should do that now. Yeah, we're gonna throw them out. So if you also want to take them back home or something, you should do that. And then other than that, be back at 11. Yeah.
Is it coffee now?